Let's continue. Any questions? Okay, I have one more problem just to get used to these integrals and waves. And then tomorrow I'll start the next new section. Okay. So this is problem 2.21. And the problem says, given initial Gaussian wave packet so somebody prepared psi of x for us at t is equal to 0, and it is given to be some a times e to the minus a x squared. And the question is asking us to normalize psi and find psi of t. Normalize and find psi of x comma t. Okay, simple stuff. So let's first normalize. So we need minus infinity to plus infinity dx psi x comma 0 squared to be 1. And this thing, if I'll assume a to be real, so this is a squared minus infinity to plus infinity dx e to the minus, there is square 2a x squared. Good. And this is the Gaussian. I think everybody here should know how to take Gaussian integral, right? So this is not kindergarten anymore, and this is the simplest thing. Actually, I've been told somebody wanted to work with Feynman, but he was worried, and he went to him and he said, I am interested in your work, but I don't know functional integrals. And Feynman told him, oh boy, there is only one integral and I already took it. And that integral is Gaussian integral. Okay? So if you don't know how to do it, please learn it. We went through it many times. And as soon as you see this, I think it would be nice if you can write the result. And in the exam, I don't care how you drive it. As soon as you see it, you can just write a squared pi over 2a. Good. And if you want to, I always forget if it's pi or 2 pi, and I can always verify if I want to. So this is 1, and this gives immediately a is equal to 2a over pi 1 over 4. Now B is a little bit more tricky. Find psi x comma t. So how do we do this? What was the algorithm? What's the procedure to follow? Yes? Can you speak up? But in the case of like continuous k, right? We have like a continuous system. How do we implement this linear combination and this time dependence? Yes? Exactly. We find the Fourier transform and then write the exponential forms there. So let's first find Fourier transform. Phi of k, let me try it, ek is equal to minus infinity to plus infinity. So this is dx over 2 pi psi x comma 0 e to the minus I kx. And once we do that, okay, I am going to calculate this phi of k in a little bit. And once we do that, psi of x comma t is going to be integral from minus infinity to plus infinity dk over 2 pi. This is going to be phi k. This is going to be e to the I kx. And this is going to be e to the minus I over h bar squared k squared over 2m times t. So this is exactly your linear combinations, but in continuous variable k. Good. Now let's calculate this. Phi of k is equal to minus infinity to plus infinity dx over 2 pi. I have normalization. This is 2a over pi to 1 over 4. And I have e to the minus alpha x squared. Now I wrote this object. And minus I kx. Good. Any questions? Any comments? How about this integral? How do I take this one? So there's like x squared, and x. Anybody? So there's, But right now our job is just to take this integral, right? Everything is given in this integral. Exactly like Gaussian, we have to take this integral. And there's only one integral, and it's already taken. So we have to play with this to put that expression in the form we know. So let me do this. So I'll play with this. E to the minus a x squared minus I kx is equal to, first I'll take a parenthesis. So let me just write this and push this guy and push this guy. First a parenthesis. Since I have a here, I need to, there's also minus. This is going to be plus and a. And I am trying to, like, what I'm trying to do is, I'm trying to do so-called completing the square. So this thing, I'm thinking about this, like some, I don't know, alpha x squared plus beta x. And I'm trying to write it like some x plus gamma squared delta. Once I do this, this is Gaussian integral. You'll see. So I'll multiply with 2 and divide by 2. And I'll add square of this ik over 2i. And square of that thing is minus k squared over 4a squared plus k squared over 4a squared. Now this piece is complete square, and the rest I can take it out. So this is e to the, there is minus a multiplying this, minus k squared over 4a. So this is equal, and this is e to the minus a x plus I k over 2a squared. So there is a here, there is a square here, right? They cancelled. Now put this back in here. So this integral is equal to, so there is nothing about integrals, so this factor is going to come out. So this is dx over 2 pi minus infinity to plus infinity. So this factor is exactly the same. And this is e to the minus a x plus I k over 2a squared. Now I can change the variable. Let's define, I don't know, u is equal to x plus I k over 2a, and du is equal to dx, and this entire thing is going to be, let me copy. So this is du. Okay, so this is du, and this entire thing is minus a u squared. And when I see an integral like this, I'm happy because that's the integral I know. So this factor is here, root, actually let's copy the entire thing. So this entire thing is here, so this is 1 over, and from the integral I have pi over a. And now I want to combine, so this is 2, and this 2 is gone, and cancel this pi with this pi, this is 1, and I can push it inside here. So I can push it, this is 1 over 4, so it's going to enter like 4 a squared, and this is going to be 1, 2, okay, this is 2 a pi, and this I think is pushed inside parentheses. Let me check, 1 over 2 pi a is good. So this is phi of k. If this is phi of k, we are done. Like psi of x comma t is minus infinity to plus infinity dk over root 2 pi phi of k, which is 1 over 2 pi a 1 over 4 e to the minus k squared over 4a e to the I kx and e to the minus I over h bar squared k squared over 2m times t. But you can see this is k squared k, this is k, and this is k squared, right? E to the entire thing is e to the minus some alpha k squared plus beta k. We can complete the square again and take the integral again. So the same integral, the same calculation, no difference. Let me define, like, okay, let me define something like alpha is equal to 1 over 4a plus so you can see I am trying to combine this 1 over 4a here and there's also here I, okay, cancel h bar, I h bar t over 2m. Good. Then this integral is minus infinity to plus infinity. These factors are exactly the same. And this is e to the minus alpha k square plus I kx. And the same thing, right? Take inside the alpha parenthesis, because we combined divide by alpha, multiply with 2, divide by 2, add this square of this minus k square over 2 alpha square, and subtract k square over 2 alpha squared. No, now the integral is k, right? Previously it was over x. So there is, I am taking the square of this object. And the square of this is minus k squared over, 4. Can you say again? X is going to be a constant. Oh, yes. Thank you. Got it. Yes, got it. You are right. Let me take it back. I don't know what I was doing. Yes, good job. So this is like I x k, right? Now divide by, yes, absolutely. You are right. Yeah. So this is 2 over 2 and plus x square over 4 alpha square minus x square over 4 alpha square, right? Now that's correct. Thank you. I appreciate. And I'll take this out. So 1 over root 2 pi. Let me write my factors first. I have this guy and I have e to d. So this thing is going to come out as, I think square of I is going to be minus here plus here. And this is going to be minus x squared over 4 alpha, and the rest is integral. So this one, so there's I x over 2 alpha. If you square it, right? This one is complete square, and this one is plus, right? Because this is minus, I need to add the same thing, but this plus and this minus are going to give, yes, thank you. So this is dk e to the minus alpha. Let me also change the variable, right? This is now u is equal to k plus I x over 2 alpha, and du is equal to dk, so du, so this is u squared, and this is the end of integral, so this is this guy, and this is going to be pi over alpha. And what did we call alpha? Alpha is this thing. Let's also write it here. Good. Let me check. 2 pi. Yes. So this will cancel this thing. Okay, let me rewrite this in terms of I define some constants. I said let me some constant TQ. I called it quantum time. If I define it like m over 2 h bar a, and also in the second set I can take a is equal to 1. I can write all length scales in units of a. this thing, okay, if you want, this is your exercise. I think this is correct. What I found is this is 2 over pi 1 over 4. This is 1 over, you can see there's t and everything will be nicely combined. T over tq times I, and this one is e to the minus x squared 1 plus I t over tq. So this is, let me push this down a little bit. I'll sketch this function, play with it a little bit. So let me write this psi x comma t. Good. So let's plot it and see how it looks as time evolves. First, let me define a psi. Is this good enough? Should I make it bigger? Maybe I can make it. So psi is going to be a function of x and t. And I will also, wherever I see t over t quantum, I'll write t. If you want, time is measured in units of quantum time, and t quantum is written here. And this thing is equal to, there is this normalization, 2 over what? Pi to 1 over 4. There is 1 over root 1 plus I t. Wherever I see t over t quantum, I write t. And here is exponent minus x squared. And we are going to divide it by 1 plus, is that correct? Yes. 1 plus I times t. I need to put like a space. I think that should be it. And I want to plot. Because this is complex, mathematics I can not plot both real and imaginary parts. I'll do absolute value. Psi x comma, let's put t is equal to 0 initially, and x goes from, I don't know, minus 10 to 10. And I also need to do, okay, plot range, I don't know, let's do from 0 to 1. Good. So that's the function. Actually, let's do minus 0.1 to 1. Okay, a little nicer. And now I want to move time a little bit. And actually, let me try this manipulate one more time. Manipulate. In my office, this works, but last time it didn't work here. And t, I want to call it t is equal to from 0.001 to, I don't know, 10. And here I need to put t. Manipulate. Okay, good. Now it's working. So this is t is equal to 0. I increase time a little bit. I increase time. As you can see, this wave function is expanding, expanding, expanding. And as time goes bigger and bigger, it's getting flatter and flatter. So let's also look at complex structure. So we have this thing. This is absolute value. Because you start with like a wave packet, right? This wave packet expands in time. That's the result of Schrödinger equation. The reason is Schrödinger equation, right? We solved it and we calculated all the things we need to calculate. And it gave us, you can see this part is the width of this thing. And it's expanding over time. So let's look at the real and imaginary parts. So this is real. And this is, I think it was something like im. Okay, let's try. If not, I can check. Let's go in time. Okay. Now I need to do, so this is real psi, imaginary psi. And this plot range, I need to do it from -1 to 1. Okay. So for some reason, this is the real part. This is the imaginary part. Okay, I think I didn't put comma, that's why, here. Okay, now I think they're all here. Okay, good. You can see this is real and imaginary parts. The norm is blue and it is expanding over time. I think orange is real part and green is imaginary part. They continue their, you can see it's doing some complex evolution. And as it goes in time, So I didn't change anything. So this is exactly the here wave function. I wrote it. This is exactly what we derived. And what I'm plotting is absolute value. Take this wave function and sketch absolute value. This is the real part and this is the imaginary part. And blue is absolute value, orange is real part, and green is imaginary part.
What is your reference point for
I mean, 0 is, so this wave function is given to us as the starting point, and that's my reference point. And I evolve from this wave function. And this is like a perfect Gaussian at the beginning. And as time evolves, Schrödinger equation scrambles this Gaussian. And you can see what it does is it's just expanding from -infinity to +infinity. Good. Any questions or comments? Maybe I can give you the rest as an exercise and finish it there. So we have, actually we can do more with this. So these are your exercise. We can also calculate norm psi x comma t. So this is the probability, right? Probability of electron cloud as a function of time. And what you are going to find is it's, if you introduce something like W, I introduce W is equal to 1 over 1 plus t squared over t quantum squared. And find psi of x comma t. The probability I found is 2 over pi. I think I may have missed some factors, but let me write so you can check. E to the minus 2 w squared x squared. And as you can see, so the w is the width of the Gaussian, and as t goes to infinity, the width is increasing, and as a result, the wave function is expanding.
For that maximum breadth time.
So this is x. This is position, and time, I am tuning the time here. If you want, I'm playing a movie for myself. Time is the third parameter. Also, okay, calculate x, but I think you can immediately answer what average value of x is, right? For a distribution like this, what is the average? What's that? Huh? It's 0, right? It's symmetric. Find, but you need to verify that. P, you can also calculate P from like derivative, but we know we can also do this. D dt times m, but because average is 0, it is going to be 0. But these are a little bit harder, right? What is x squared and what is p squared? And from here you can check sigma x, sigma p bigger than h bar over 2. And see if uncertainty is obeyed. Good? Any questions? All right, thank you. I'll see you tomorrow.